So here's a presentation I did at the Cyclitech Conference back in December 2016. The Cyclitech Conference was a cycling technology conference. You can just Google Cyclitech and it'll come up with the details and speakers. But there was a whole range of topics there. Bicycle design and material specifications and repair and helmets, e-bikes. The UCI was there. Savello did a presentation. There was a whole range of stuff. So this is my presentation: ultrasonic inspection of in-service composite bicycles and components. And by in-service, we mean in use as opposed to production, although I do touch on production towards the end. So here's the presentation, and yeah, put any comments at the end. So it's just a little bit of personal background, qualifications, where I've worked, certifications, etc. Founded Luescher Teknik in 2008. So Luescher Teknik is my company, and we are a specialist sports technology company. We consult on a range of engineering, so like sport engineering, but mainly with composites and quality. Some of the bigger projects we've had is we designed the Melbourne Star Oppie range of carbon bikes, the Baumeister Composites Tamar mountain bike enduro rim. We've also done other work with archery and hockey and a few other things like that. We've started up the bicycle assessment and repair division in 2009 from demand from people were saying, "Oh, I've crashed my bike. Is that something you can do? You can repair?" And I said, "Yeah, absolutely." And then insurance companies approached us for doing damage assessment with ultrasound scans, etc. We did some warranty stuff for brands, distributors, etc., different bike shops, and walk-ins from the public. So what is NDI, non-destructive inspection? So it means to inspect the material or parts without affecting the function or performance. So it provides the information on the integrity, reliability of the part, and it's a quality assurance method. So the ultimate goal is to provide safety of the components in use. So different NDI methods for composites. We have ultrasound, which I'll talk about primarily today. Radiography, X-ray. Acoustic emission is another one that's used. Thermography is also used. The tap test is a common one. I'll talk about that in a minute. And don't underestimate a good visual inspection. So what is an ultrasound scan? Very basically, you send a very high frequency sound wave through the part, and you listen to what is either coming back in this case, or what's transmitted through the part. So if we look at this example, we've got the material, which is that's the thickness through there, and that's represented by these peaks across there. So that's your front surface, and that's your back surface of the part. On this example here, we've got a defect, and that's represented by this peak here, which is approximately mid-plane. So the sound is reflected off that interface, and that's shown on the oscilloscope trace. So why do we use ultrasound? We use it because it's very reliable in finding these sort of typical defects in laminar products, as most composite materials are. So the some of the advantages are it's relatively low cost. The equipment is not out of reach of a lot of people, and it's safe to use. You don't have, like with X-ray, you need to have exposure bays, and you've got ionizing radiation, which is very dangerous, all these sorts of things, which adds to the cost of those methods as well. And it's also very quick, so you can put the transducer on the part and you can get a result almost instantly, whereas again with other methods you need to process films or have exposures or this or that. So there's a whole range of advantages for ultrasound. So the different types of ultrasound, you've got through transmission, which is being done in this example in the photo. You have pulse echo, you have compression waves, shear waves, A scan, B scan and C scan. Now an A scan is what we'll primarily be talking about in this presentation, which is the raw oscilloscope trace at a point source. The B scan takes a slice through the part and has you create an image from that data. So you've got the same basic waveform, but it's how you display that. So the B scan displays that as a slice through the part, and a C scan displays that as a plan view of the part. So here is an example of a C scan. So that's a plan view of the part, and you can see that there are different indications on the part. So there's a red indication and there's blue indication. So that highlights different aspects of the scan. So those blue indications, typical of a delamination or something like that. So the energy is dispersed into the part. So we can tell, the thickness, the type of damage, whether it's a delamination or a void, unbond, or a fiber wrinkle or inclusions, etc. So we can all tell that from the characteristics of the signal and the trace. So within service ultrasound, we typically use A-scan pulse echo because it's portable, it's quick, it's very suitable for variety of the variable geometry that you get in a bike frame. So due to all the curved shapes and junctions and these sorts of things, it's very difficult to produce a C scan of that type of product. It's also very difficult to do a through transmission because you need access on both parts. So if you've got a small diameter tube, you can't get a transducer inside that tube to do a through transmission. So you typically use pulse echo A scan. So it doesn't produce a hard copy or image. You can do a recording of the trace. However, that's sort of typically not done. It's more dependent on the experience of the operator or technician doing the scan. So it's how they interpret that oscilloscope trace result. So here we have another example of a A-scan pulse echo. So access is only required from one side, so it's a single transducer. In this case, it's like we're looking at a flat panel, but it's suitable for the variety of geometrical shapes and contours. Now there is no sort of typical image like you get with an X-ray or a B scan or a C scan. So the interpretation is directly off the oscilloscope trace, which, as discussed, requires experience. If we look at this particular defect here, which is approximately mid-plane of the part, and so it's coming up right about here. So it's about half the thickness of the part. So if the back wall was sort of coming up at around a depth of 6, here it's coming up at about 3. So we know that the indication is about halfway through the part. The other thing we can tell is that because the amplitude of that signal is quite high, that the that flaw or defect is a good reflector of sound. So something like a planar void or a foreign object which is very reflective will give us that amplitude. So from the amplitude of the signal we can tell what type of flaw or defect that might be. So here we have a typical ultrasound unit. It's this particular unit. It's an older unit, but it's still a very good unit. It was aerospace level the ultrasound scan equipment. It's capable of doing pulse echo or through transmission at a range of different frequencies. We typically use smaller transducers for bicycles because they can handle the geometry in the contours a little bit better. This unit's portable. It's battery powered as well. There are smaller, more portable units around, but the what makes a good ultrasound set is the amplifier. So you're basically looking for an amplifier which has a very good signal to noise ratio. So you're trying to amplify very faint sound signals effectively, and so the quality of your amplifier is what it's all about. So cheaper units will have an amplifier which isn't as good, and then that sort of compromises some of the things and the capacities of what you can find and see. So why not just use the tap test, or the coin tap test is what's commonly referred to, and even some of the brands, they refer that in their manuals, just tap it with a coin. The truth is that the tap test is quite unreliable for laminate testing, particularly on bike frames which have variable geometry. So the geometry and the thickness of the material has a significant effect on how effective the tap test is. So a tap test is it is an aerospace certified process, but it's typically used on flat sandwich panels like honeycomb panels with thin carbon skins, and it's good for finding core to skin disbonds in that sort of situation. But a bike frame is a much different different scenario, and so what we find is that it's very difficult to accurately size and assess a flaw or damage. So typically the damage, if you have visible damage, it may tap, and that's sort of about about sort of what you can use it for, but then you can see the damage usually visually anyway, so it just sort of confirms that. So it certainly hasn't got the sensitivity to find a delamination within the laminate and accurately size that. So why do we need NDI? So the purpose of NDI is we want to find damage or production flaws that can lead to an in-field or in-service failure that can cause injury or even death of the rider. So if a fracture critical item of the bike fails, like a fork steerer or a fork leg or the head tube, leads to a catastrophic failure. And So what we're trying to do with NDI is find flaws or damage, such as over tightening damage, etc., and find those areas of damage before the part fails and causes an injury or death. So the effect of flaws. So flaws in the laminate, such as voids or porosity, have a significant effect on the properties of that material. So if you have greater than 2% of voids, your flexural strength can be reduced by 20% or even greater. So there's lots of documentation on this over a long period of time on the effect of flaws. Lots of testing has been done. But basically, these flaws reduce the mechanical properties. So if you've designed a part to require a laminate thickness of X, if you've got voids in there, you don't have the strength or the stiffness that you think you have, and the part could therefore fail at a lower load than what it is designed to experience. So flaws in the part reduce the mechanical properties. So as I said, it changes the design load capacity versus the actual load capacity. So in this case, this is Mark Cavendish sprinting off the front. His front wheel has collapsed and he's about to bring the whole bunch down. I mean, the rider behind him hasn't even seen that he's gone down yet. So one of the things that we've seen a lot over the time is that if there are flaws in the part, that even a lower level impact can lead to greater damage within the part. So by avoiding these flaws or handling damage or any of these sorts of aspects, you get better life out of the part, better durability out of the part, and higher safety out of the part. So we've had a searchable database for quite some time, and at the time of the presentation, these are some of the stats. So the big ones was obviously crash damage, but there was quite a large percentage of manufacturing flaws and handling damage as well. So the other aspect, which is almost a quarter of it, is things like chain drop and tire rub. When tires, when the trend in tires went to sort of larger tires, from 21 to 23 mil tires over to 25 mil plus tires, some of the older frames didn't have enough clearance through the chain stays or the seat stays, and people were wearing holes in their frame from using these bigger tires. The other thing that we found is rear derailleur hanger failure. So the replaceable rear derailleur hanger fails and leads to an impact, the derailleur impacting usually the seat stay, but also sometimes the chain stay and causing damage. So they're some of the primary things. The other ones, over tightening parts, roof racks is quite popular as well, and then the baggage handlers in transit and that sort of thing. So as I said, crash damage is the most common, and seat stays and top tubes are probably the most common areas of damage. And there's a number of reasons for this. Those tubes are quite light structurally, so the loads in those areas are less than other areas of the frame, so the wall thickness is thinner, and so they can be damaged easier. Also, those tubes are quite exposed, like the top tube. The handlebar will swing around in a crash and impact the top tube, or a seat stay is quite exposed. So those areas tend to receive the worst of it. Fork steerers, we often see delamination in a fork steerer after a frontal crash, and that's usually not visible. And the tire rub wear, as I said before, and due to the wider tires. So we'll run through some examples. Obviously, this frame is sort of damaged a little bit beyond what's sort of typically a practical repair, but we'll show you some of the things and that we see. So here we have a fork steerer, and you can see quite a large planar void sort of in this area through here, and it's sort of in the middle of the steerer, and it's a result of poor compaction, and basically the pressure hasn't consolidated the laminate sufficiently in that area. Now there's no visible indication on the surface of that, and due to that, the area of the void and the location being approximately midway between the bearings, sort of it's a high bending load in that area. So in this case, it was scrapped. So another fork steerer, and you can see several areas marked in the yellow crayon there, where we found again some planar voids. Now this is past a CT scan, and there was no visible indication of any flaw on the surface, but the passing a CT scan. Now the difference between a CT scan and an ultrasound scan in this case is the ultrasound scan will find damage where there's a sound interface, where with a CT scan being basically an X-ray type process, you're looking for a change of density. So if a void has got a very low volume, the void won't show up much of a density change, which makes it very difficult to find. So, but without knowing the accept or reject criteria from that scan, or seeing the raw data from the scan, it's hard to speculate. But yeah, there are limitations to each method on what you can find. So here's a fork crown in this case, and again some more planar voids, and sort of along this edge through here. And obviously the fork crown is a very high load area, and so then this fork was scrapped. So again, there was no visible indication on the surface of the part that this flaw existed. Again, yeah, this one was scrapped. Here's another fork crown, and this time it has some wrinkles. So quite heavy wrinkling going on, sort of through here, and also here. So a wrinkle is it affects the load path, because what's happening is it's sort of like a rope, in that the fiber can only take load along the length of the fiber. So if you have a bend in the fiber will want to straighten out before it can take the load. And so, example through here, if the load is going along there, well, the load path now is sort of going through like that. So you have lower load carrying capacity and lower stiffness. So a wrinkle is a real problem. There's also porosity associated with it. You can see some voids even there, but there's porosity in these areas through here and through here, also through here. So yeah, this was another scrapped item. So these were found in the scan, and then the part was sectioned after it was scrapped, obviously. So here we have another fork steerer, and this one was involved in a crash, and there's quite a large delamination marked in yellow. So for a delamination to occur over that large an area, so the stem is clamped here, and you can see the compression ring for the upper headset bearing was here. So you've got this bending force. Now, it's highly likely that there were voids and porosity, through that area, which then, basically popped when the impact energy was dissipated. So these voids and porosity, they act as stress concentrations, and will then that will propagate through the laminate. So again, there was no visible indication of this delamination, but this fork was scrapped. This one's a little bit more unusual in that we found some resin dry fiber during the scan. So what that means is basically the fibers aren't encapsulated in the resin. So there's loose fibers. So you could basically pull these fibers out of the part. Now this is quite difficult to find with most methods. Like with an X-ray, there'll be very little density change. However, with an ultrasound scan, you'll find that the back surface will not reflect as much, and so you have a lower back wall signal, which you need to be pretty switched on to catch that, but it's possible to do that, as was in this case, and then this one was therefore scrapped. So here we have a frame seat stay which the rear derailleur hanger has failed, and the derailleur has swung around and impacted the sort of above the dropout on the seat stay. So the question is it damaged or not? Is there underlying structural damage, or is it just a paint chip? So with the ultrasound scan, we can do a scan and get a yes or no answer in a very short period of time. So in this case, there was no structural damage, and it was just paint only damage, so the bike was safe to be used. Another common one is chain drop. So with some frames, the clearance between the crank and the chainstay is such that when the chain gets sort of wedged in there, it really creates a large delamination. So in this case, there was a sort of a small visible gouge, or smaller visible gouge, but then the area marked in yellow and yellow crane was delaminated. So as you can see, it's quite a substantial area that was delaminated compared to what you visually can see. In this case, there was this damage was repairable. In some cases, the delamination can travel sort of all the way through into the bottom bracket bond, which then makes the repair much more difficult, or sometimes not practical. Another case of chain drop, and in this case, there was some visual surface damage to the paint. However, the scan revealed that there was no underlying structural damage. So again, this one was you could do a paint repair just to seal the surface again, and yep, no underlying structural damage noted. Now this is an older Trek, the Trek domains, or the 5200s series. So the older Treks from sort of the Lance days, to the late 90s, early 2000s. So it was really common to get a crack indication. You can see that sort of through here at these lug joints. So typically the factory, you'd go back to the factory and say, oh, my bike's got a crack, and they go, no, it's just a paint crack. We see that all the time, and it was common. It was a very common thing, and a warranty would often be rejected based on the visual inspection. And sometimes they might do a tap test in a bike shop, or back at the dealer or whatever. In this case, the customer brought it in for a scan, and when we scanned it, and I'll show you on the next slide what we found. So here what we found a very large void in the adhesive joint through here. And there's a very small bit of adhesive just at the edge, and that's what's led to the crack indication, because there's no adhesive really backing it up. So that adhesive void is quite large, and so when the part was used, that area would flex. The other thing of a real concern we found was this area of wrinkling sort of adjacent to that junction. So this is the down tube to head tubes junction. So it's a very, very high stress area on the bike, and you can see also some porosity sort of in this area through here. So there was a whole bunch of areas that are structurally compromised. So this bike was scrapped. Another common thing is bridging voids. So where you have a corner on the tube, and basically the sharper the corner is, the more likely you are to get bridging voids. So bridging voids are where, when the fiber's being laid into the tool, into the mold, that the fiber, you're not getting it right into the corner. So when it's cured, you have this void along the corner of that section. So in this case, you can see marked in yellow the series of bridging voids, and then there was a crack. So the crack indication was also here, which was what the customer originally brought it in for. So again, when we scanned it, we found all these other areas of bridging voids, and so it's clear that the crack indication was presented itself due to those voids. So in this case, we could repair it. We could rebuild that section of the bike, sort of. So all through this section on that corner was repaired. Another one that we have is we have a combination of an impact and planar voids and porosity. So in this case, the top tube was impacted, but because the laminate quality was quite poor with planar voids and porosity, that basically the entire top tube, the whole face of the top tube delaminated. So that was beyond a practical repair, and the bike was scrapped. So sort of an example of where you've got production floor combined with an in-service impact or yeah. This one was caused by a roof rack carrier clamp. So the bike was mounted on the roof rack. The clamp goes around the down tube, and the wheels are still on the bike. Most people are familiar with those types of racks. Now, delamination was found, marked in yellow, so quite a large area. There was almost no visible indication of the surface. Very fine little crack on the corners, but the damage area was much more substantial than that. This one was repaired and put back into service with no issues. Other areas of laminate porosity, and so here we found some large areas. Now this is actually a Cervelo, the California. So one of their handmade ones, which ended up, I think they were selling them for about $10,000 a frame or something like that. Now there was no visual indication on the surface, but these large areas of laminar porosity were found. So there's a number of reasons or causes for that during production. Now I did liaise back with the Cervelo engineers on that, and gave them feedback on the scan, but this frame was scrapped. We have another frame down tube, and this was involved in a crash. It's the down tube and near the head tube junction, and the brake caliper impacted the frame sort of as the fork turned around. So there was delamination. There was basically no surface indication, very light little scuff on the surface clear coat. But as you can see, the delamination is quite large. In this case, it was repaired and the bike was put back into service without issue. Now this is a really interesting one, because originally the customer brought the bike in because he was concerned about this long indication through here, and so I took the front derailleur clamp off to scan it to get a better access to the scan. The original sort of crack indication was just a deep paint scratch, and there was no underlying structural damage. However, the scan found that the front derailleur clamp had been over tightened, and as you can see, this area marked in yellow through here, there was quite a large delamination. So then that was repaired, and then we repainted and did the paint repair on that other area at the same time. The frame cable stops, you often see delamination where the rivets go through, and sort of combination of poor drilling and poor rivet choice. Now this has improved, so that better rivets are being used. So instead of the shank expanding, the shank just pulls down. And often fabric is used on the internal surface to prevent this sort of splintering of a unidirectional laminate, like has happened in this case. So, so these can be repaired. We can remove the rivets, do a repair on that, and then reattach the cable stop using correct rivets and adhesive. Now here we have you call it a dog's breakfast. It's quite a mess. This is sort of the head tube, down tube junction on an older bike, and you can see a lot of variation in wall thickness, and there's lots of resin pooling and variations in the compaction. There's fiber wrinkles. Now this is sort of quite common in the older bikes, and you'd get it was quite common to see sort of cracks appear over time of use. So, you know, obviously at the root of a wrinkle, or due to the changing in stiffness due to the fiber variations and the resin pooling, cracks would appear in some of these older bikes. This is a wheel rim, and it's a tubular rim, but it's had an impact, and you can see the impact sort of right here. When we scanned it, the delamination, as marked in yellow, is much more significant than just what the impact looked like visually. So it goes all the way to the spoke access hole and past the brake track. So this, in this case, it was scrapped. Other cases where the rim damage is limited, like if it was just what you'd see visually, you'd be able to repair that, but the delamination is the main damage here. Another rim, this is a lightweight rim. Now these are made with very thin carbon skin over a foam core, and so in this case there was some damage to the skin to core. So the core crushed and desponded from the skin due to an impact. So it was a very small sort of depression on the surface, and then the area marked in yellow was desponded. So in this case we could repair that, and the wheel could go back into service. Now, handlebar drop. Now this handlebar was sent in because the other side actually failed during use while the person was riding along, and so it was sent to us to assess why it failed. But then when we scanned other areas of the bar, so the drop on the other side that didn't fail, we found, you can see all through this bend here, there's planar voids. Also through this end, through here, you can see large planar voids. Porosity through here. You've got resin pooling. So there's a whole bunch going on. Poor compaction, large voids. So it's not surprising that the handlebar failed with those flaws. Here's another handlebar, and this is the stem clamp area, and you can see a void through here. Now, the area marked in yellow, it's a little bit hard to see on this photo, but it sort of goes from around through like that. And so basically this void acts as a delamination initiation point. So then once the part was under load, it was overloaded from tightening, over tightening the stem, that void then propagated and created this large delamination. So there's no visible indication on the surface, and but in this case obviously the handlebar was scrapped because we cut it in half. And so it's important to not only tighten your stem clamp correctly and evenly to the correct torque, etc., but also to make sure that it doesn't have any stress concentrations points on it. So that the stem has nice round corners, etc., like no sharp edges that really can lead to sort of pinch failures and other problems on the handlebar. Again, another stem clamp failure on the handlebar. So it was very slight depression on the surface, and again this was over tightened. So with stems you need to make sure that the the diameter of the stem matches the diameter of the handlebar. If it's undersized, it'll be more pinching and more likely to cause a problem. So that's something you really need to take note of. And as I said before, make sure the surfaces, are rounded and there's no sharp corners. So this one was scrapped. So to quickly summarize a lot of this stuff, the flaws are primarily process related. So if you use the same process, you're susceptible to the same types of flaws. The better quality assurance is required to prevent these some of these in-surface failures. So if there are voids or porosity or wrinkles in the part, these should be identified during manufacture and not during in-service failures. Delamination is mostly not visible on the surface. Same with planar voids, these sorts of things. So they're very difficult to see from a visual inspection on the surface. You often need more information than that. So what we find is that warranties are like the brands will just say, well, if you say we find a void in the part, well, and often the brand will say, well, the part hasn't failed, and it's like, well, so what? The part needs to fail and someone needs to be injured before you accept that there's a problem with the part? Clearly on these scans we can see that the part is structurally compromised, and we shouldn't need to wait until somebody gets either injured or even killed before they accept that there's a problem. After a part has catastrophically failed, it is more difficult often to find evidence of a flaw. So if you have a void and then a large area is delaminated, it's very difficult to find that void, which was most likely the initiation or the trigger of that failure. So we'll just quickly touch on production NDI. So what is it? So it's basically revolves around process control and having a feedback loop to show that your production process is performing as you anticipate or expect it to perform. So the purpose is to reduce in-service failures. Now, the advantages of reducing in-service failures is obviously your customers don't get injured or even killed, which will affect your brand reputation. You can have recalls, which are very expensive, and again, they affect your brand reputation. You've got warranty claims, liability, and so the basic sort of principle is if you provide higher quality, safer, better parts, your overall costs are going to be reduced, because you won't be having to pay out warranty replacements, you won't be having to do recalls, you won't be in court showing liability claims and personal injury claims and things like that. So overall, if you're looking at the big picture, quality wins. So people will buy quality parts to ensure that they they don't get hurt or killed doing what they enjoy doing. So that's the presentation. You can check out the website. I do have a lot of technical articles on the carbonbikerepair.com.au website. You can contact me at info@luescherteknik.com.au, or you can leave comments at the end of this video. Okay, hope you learned something, and we'll see you again soon. Okay, bye.